Right. Welcome all. So let's start a concept series where one important concept from the production technology for the GATE and engineering service examination I am going to discuss. Whereas production is one such a big subject where we divided the entire subject into parts. In that, yesterday in a preparation strategy, especially I talk about metal cutting, machining and metrology. Whereas out of entire production syllabus, as we have a number of manufacturing processes, we know that one of the highest weightage subject ever in any competitive examination for the mechanical engineering is concerned. So what this particular 1 hour agenda is, I will take one topic and in detail discussion of that topic I am going to make. Almost I can say from the basic metal cutting principles, I am going to give you idea about orthogonal machining operation. Whereas when we mention metal cutting operations, in metal cutting, we actually want to remove the excess unwanted material from the workpiece to get the final geometry of the workpiece. To do that, we use the single point cutting tool or even multi-point cutting tools. With the help of that, in a conventional machining operation, we engage a workpiece and the machine, and with a physical contact between tool and workpiece, we try to remove the excess unwanted material so that we try to generate the final surface what we need. For that, as metal to metal physical contact, so we prefer to have always a basic shearing mechanism should happen on the workpiece material with the help of tool. The reason is, out of various type of forces, on the metal, if it is a shear force, it is the minimum force required or minimum force sufficient to break the crystal structure compared to any other force. So in that way, we need to create the geometry of the tool. Right. So by using a very good evening, little time we take before starting. So I hope everything is clear. Good evening, sir. Right. So as I said, in a metal cutting, we are going to remove the excess unwanted material with the help of tool. So understanding the tool geometry is very, very important for us. Whereas the single point cutting tool, many people know that in a metal cutting operation, one diagram, we call it as the wedge shape of the tool and the workpiece material. But the question is how this particular diagram we are going to obtain, and why the workpiece motion is towards the left to right, and why this wedge shape of the tool, and most of the people don't even aware what actually angle is, and how this plane we are going to obtain. And when we are saying this is the machined workpiece surface we are obtaining, machined surface of workpiece, then what is the role of tool geometry and why this figure, especially when we talk about principles of metal cutting, where we initially discuss cutting forces and the velocities, so that our major focus will be always a calculation of the total power. So the total power, which is nothing but the cutting power, always equal to cutting force into a cutting velocity. Cutting force into cutting velocity. So force, which is what the shear force which we apply, due to that we try to separate the material, but to perform the shearing, the resultant what we are imposed on the tool, on the workpiece from the tool, which give in the direction a cutting force. Or we can say cutting force is the measurable force which is the algebraic summation of all horizontal component in this direction. And due to this dynamic nature of a machining, will perform the shearing in this direction, where shear force appear in this direction upon the cutting force. So shearing helps to separate the unwanted material. Now question is, if you notice here cutting force in Newton, cutting velocity V also again in the same direction, which is in a meter per second. So Newton meter per second, if you observe, that will be joule per second, which is nothing but a watt. So power calculation in what we try to perform, and then that total power calculation we try to minimize. That is what the basic objective of the entire metal cutting principles are. And with a minimum power consumption condition, we create the tool geometry so that in any kind of conventional machining operation, not only on the plane turning, many people feel that this figure came out of the plane turning. No, even it may be a single point or multi-point cutting tool. In every machining operation, you can go on the orthogonal plane and you can able to project the same variety of the tool and workpiece projection. But the thing is, person need to aware how this projection of the tool and the workpiece we are going to get, and for that we adopt as of our syllabus plane turning operation. From that we try to discuss first of all tool geometry in our regular classes. But here one concept I need to discuss. For what I try to do is the tool geometry whatever we have. For example, if you notice, this is what the single point cutting tool we create. In that we used to have a 3 different projection. One is the front view, one is the side view, and another is the top view. So based on that front view, side view, and top view, if you notice these planes what I try to show here, those are the planes which are perpendicular to each other. And when you make this tool for the plane turning operation, in plane turning what happen? We'll hold the workpiece material. For example, this is the workpiece in the headstock, whereas workpiece material is now rotating with respect to its axis, and rotational speed will be provided, which is a certain RPM, and there will be a standard. And in this tool geometry, there is a theoretical tool and even practical tool geometry conditions. We have theoretical tool geometry where we used to draw the sharp wedge shape without having a curvature. But still, we try to show the side cutting edge angle and end cutting edge angle. And the projection of the tool in the front view, side view, and the top view, which is giving us this is what the figures where ASA tool signature we used to discuss initially for definition of the angles. In American Standard Association, we are using 3 mutual perpendicular plane. First plane which is perpendicular to the base of the tool. If you draw this way, the figure for the workpiece and the tool material in plane turning operation, it's a top view where we call entire this plane projection is on the reference plane. So this projection where we are noticing the tool and the workpiece top view is the reference plane. So shall I say this projection of the tool what we are getting that is on this plane, which is the plane parallel to the base, or we call it as the reference plane. So with respect to the reference plane pi r, we have 2 planes. One is a plane perpendicular to the base lengthwise with a tool and even widthwise with a tool. So lengthwise with a tool is nothing but this is what the plane direction, and widthwise with a tool is nothing but this is what the plane direction. With respect to the reference plane, one is a plane perpendicular to the reference plane lengthwise and another one is widthwise. The plane widthwise with a tool become parallel to the workpiece axis. So as it is parallel to the workpiece axis, therefore we call it as the longitudinal plane or pi x plane, and the plane which is lengthwise for the tool become perpendicular to the workpiece axis. Therefore we call this one as the transverse plane or lateral plane pi y. Therefore, based on these 3 planes, reference plane, pi x plane, and pi y plane, we make the projection. One is a longitudinal plane and another one is a transverse plane. So based on these 3 planes, when you make the projection of the tool, that is what a front view, side view, and the top view, that projection comes under the ASA tool geometry. We call it as American Standard Association based tool representation. In that we used to discuss back rake angle, side rake angle, then end relief angle, side relief angle, then end cutting edge angle, side cutting edge angle, then nose radius capital R, that is in mm. Whereas definition and measurement of the angles are very easy as far as ASA tool geometry is concerned. But remember, to perform the analysis means to draw this figure, we need to know after ASA even ORS tool geometry. ORS tool geometry where we used to take other than longitudinal and transverse plane, with respect to reference planes, those planes we consider where analysis can perform very easily. Or you can say projection of the tool and workpiece together as per the ORS system, when you make, it will be easy and convenient on the plane of paper with a little assumptions. So those projection based, when you have the tool and workpiece geometry, which can be easy and convenient to calculate even power, and once you have the power calculation, so that you can reach up to the total minimum power calculations. For that, we need to study ORS system in detail. Before ORS system, we focus on the ASA tool geometry where we talk about all these angles. But in these angles, no angle is useful, especially on the plane of paper. Reason is simple. When this tool is engaged with a workpiece, then machining which is performed is the three-dimensional, or you can also call it as the oblique machining. So in oblique machining, chip is variable. After that, means when this tool is performing machining operation, at one instant when you notice, suppose consider the tool reaches up to this position. So by the time tool reaches up to this position, machining is performed to the workpiece, where after completion of machining, up to that position of the tool, workpiece look like this way. Whereas practically noticing, you also might have observed, when conventional plane turning operation is going on, chip whatever comes out which will be in a curl behavior. There will be a curl behavior of the chip. So performing analysis in the three-dimensional machining where variable velocity causes you to get the curl. Reason of getting variable velocity is the diameter inside is smaller and outside is larger. So the chip which is coming out over the width direction of the cutting edge having two different velocities. The rotational speed might be n, which is fixed, but diameter difference will change the velocities of the chip. So chip outside will come faster and inside of the chip will come very slower in rate. So suppose consider this is the 0.1 and 0.2 of the chip, whereas a chip faster will be at the 0.1 and at the 0.2 it will be slower in rate. Due to that, chip will always take a curl formation. So curl behavior of the chip and also that is due to variable chip velocity. Chip velocity is not constant, is the variable in case of the three-dimensional or oblique machining. So as a chip velocity is variable, and the two forces are not on any single plane, they are three-dimensional. So analysis will find difficult if you go for the three-dimensional machining. So what we do is, we go for orthogonal Trig system where we talk about the tool geometry representation on the orthogonal plane along the cutting plane. For that, reference plane is common, means a tool projection from the top view is common. But instead of taking previously like I draw one vertical and one horizontal line with respect to the tool, but this time we are taking, this is the reference plane projection of the tool, but this time we are taking with respect to the reference plane, I am taking one plane, we call it as the cutting plane. So what is cutting plane? In ORS system, after reference plane, cutting plane is the plane that contains the side cutting edge of the tool. And along this, we will be taking one more plane which is perpendicular to the both cutting plane and reference plane, that is in this direction. So actually this is that direction where to the tool when you provide the feed motion, effective or true feed direction on the workpiece will be perpendicular to the cutting edge. And that plane which is perpendicular to the both previous planes is called as the orthogonal plane phi naught. We call it as orthogonal plane phi naught. So projection of the tool on the orthogonal plane along the workpiece will help us to get the two-dimensional machining. It means we can make the analysis on the plane of paper. So initial two-dimensional analysis help us to estimate the cutting forces, shear forces, frictional forces, and after that all the velocities also comes on the same plane. So that forces and velocities based, we are able to calculate the total power. Once we have the total power consumption, how much it required, that estimation once we have, then we adjust the tool geometry in such a way that we create the tool geometry in such a way that we should have always minimum power consumption. So minimum power consumption is always a basic objective of any topic or any subject you take. Even here also. So based on this, when you observe tool and workpiece together, the plane which I am talking is along the reference plane. This is what the 3D projection of the tool and workpiece, where the workpiece is rotating to the tool we provided depth of cut and feed. See, already few assumptions we have here. Based on that only, we try to draw the tool this way, where the cutting edge is a straight line instead of the curvature. And that line is a parallel to the reference plane. It means if you make the projection of the tool on the cutting plane is nothing but the plane containing a side cutting edge. So this particular plane, if you take, on that plane if you make the projection of the tool, then what happens is we get one angle which is called as an inclination angle that should become a 0. So previously in a ASA tool geometry, the angle what we are getting, which is based on the transverse plane, is called as back rake angle. This one is a back rake angle. But I am not taking transverse plane. This plane little bit we are inclining so that it should be on the plane, means it should be a plane that will be containing a side cutting edge. So when I go to that plane, on that plane we are noticing a inclination angle I is equal to 0. So based on that plane, I am taking again one more plane which is perpendicular to both these planes. One plane we have that is a parallel to the base. On that entire tool and workpiece projection we made, that's a top view. And there is cutting plane which is perpendicular, and I am taking one more plane which is perpendicular to both these planes. We call that one as the orthogonal plane. So based on that plane, if I notice only a tool, then the wedge shape inside the tool what we are noticing, that is on the orthogonal plane. Means on the 3-dimensional projection of the tool and workpiece, if I make the cut section with respect to the plane perpendicular to the cutting edge, and that plane will be containing the inside that yellow color portion of the tool, and we call that portion of the tool as the wedge shape. Wedge shape of the tool. Wedge shape of tool. So on that plane, if you take the workpiece and tool together, we are able to notice something like this, the workpiece, which is rotating counterclockwise, and the tool is moving parallel to the workpiece axis, which is called as a feed motion, which is in mm per revolution. So this counterclockwise rotation and the feed motion together will be represented here, the downward motion of the workpiece. And on the tool, we are getting one angle now. If I draw here the line parallel to the reference plane, then this angle what we are getting, we call it as the orthogonal rectangle. And many people used to confuse with this orthogonal rectangle with a side rectangle, and some used to go with a even back rectangle. Unfortunately, those both are not correct. So in orthogonal or 2-dimensional machining, this angle is neither back rectangle nor side rectangle. It's called as a orthogonal rectangle. That's why in all the numericals of principles of metal cutting, it's always mentioned that it is always rake angle. In orthogonal machining, the rake angle is provided. In orthogonal machining, rake angle. If you notice recent gate questions, first of all, I will show that terminology. Observe here, in this gate question, I will go to question also later. In an orthogonal machining, this is a 2022 gate question, sir. This year. In an orthogonal machining operation, observe the orthogonal rake angle is 0 degree. Whereas if I go to one more question here, here they mentioned indirectly in such a way that the orthogonally turned such that the entire wall thickness of the tube is cut in the single pass. So orthogonal turning is mentioned. But person should have idea what they are saying. They are saying a cylindrical tube, an entire wall thickness of the tube is cut in a single pass. Whereas people even don't know that practically also we able to make the orthogonal machining experimental setup. There are two orthogonal machining experimental setups popularly we use, which is in that two, one is a cylindrical tube turning and another one is a disc turning operation. So when you consider this, with the side cutting edge angle is 0, if you take the projection on the orthogonal plane, again for this also we able to draw this kind of figure. Whereas why we draw this way means to make a easiness, convenient. Otherwise, orthogonal plane is the plane that is perpendicular to the cutting edge. So projection if you make, this is what the figure, we rotate 90-degree counterclockwise so that we able to get always something like this, tool and workpiece. So on that orthogonal plane, this projection of the tool and workpiece is in which plane? Pi naught plane, we call it as the orthogonal. So the angle whatever we have, that is orthogonal rectangle. Sometime we may use alpha, just alpha we mentioned, and instead of calling every time it as orthogonal rectangle, in the questions they mentioned simply a rectangle. In orthogonal machining, rectangle. Because anyway orthogonal plane, orthogonal machining is considered, so the angle whatever they are mentioning it's a rectangle, it indirectly indicates it's a orthogonal rec only. So either this question or even one more question, I think, here if you notice, under orthogonal cutting condition, again, all these three are this year, GATE 2022 questions. Whereas they mentioned the orthogonal rake angle of the cutting tool is 5 degree. Whereas if you are able to visualize tool and workpiece, we are able to reach here, and after this there is analysis on the orthogonal version. Popularly, we call that analysis as the merchant's analysis. One of the most important analysis where frequency of getting question is very huge. Every year minimum one question is obvious. And in the merchant analysis, we always give first of all the thickness difference between the chip before cutting and after cutting. It means before cutting, thickness which is considered is T1, which is depend on the feed provided to the tool. Either T1 is equal to F cos psi, where psi is the side cutting edge angle, or T1 is equal to feed. This is considered only if a side cutting edge angle is equal to 0. Means in the data if side cutting edge angle is not given, feed is mentioned, then always we should consider the second case. But if the side cutting edge angle is also there and feed is also there, then we should consider this. Whereas sometime instead of the ASA tool geometry, this side cutting edge angle comes in a ASA tool geometry. Sometimes directly ORS tool geometry is given, whereas in ORS tool geometry what we are going to do, we are taking a projections based on the reference plane, cutting plane and orthogonal plane. Then if you notice, the angles are like inclination angle, orthogonal rake angle, then after that orthogonal side relief angle and orthogonal end relief angle, both are on this cutting plane and orthogonal plane. Then end cutting edge angle, then the sixth position angle is a lambda, which is a approach angle, then nose radius again will be there, that is in image. So this approach angle is the angle for the side cutting edge in the feed direction. Means this is the side cutting edge angle in the top view, whereas this one will be the remaining angle to the side cutting edge angle, which is always 90 minus psi, we call it as the approach angle. So sometimes ORS system if they give, then the uncut chip thickness will be F sin lambda also. Simple logic, instead of psi if you substitute 90 minus lambda, then it will be a F sin lambda. So any one of these two equations only we should use to calculate the uncut chip thickness. So once you got the T1, then we used to proceed for the analysis to find this thickness, which is considered as a T2. Now people will get confused, sir, why the thickness difference only happened? Because we make many assumptions before starting analysis, especially in the merchant circle diagram. Means in the orthogonal analysis, we have the many assumptions. The first assumption is always width of the workpiece remain constant. Means all the width related parameters are constant. Either before cutting or after cutting, every parameter which is width related is constant. So width of chip, width of workpiece before machining, width of chip after machining, right? Everything is constant. And the tool whatever engaged here, so the third experimental setup is taking the tool and workpiece in such a wedge format where if you make the projection of the tool and workpiece, again we are able to notice the same wedge shape of the tool with one angle, we call it as the orthogonal rectangle. So after considering width of the workpiece and width of the chip constant, the only permission we used to observe, or only change we used to observe, which is in the thickness direction, T1 and T2. And along the thickness, as thickness changes are happen, that implies even on the uncut chip length and chip length also. It means before starting machining operation, the length of the chip, if you consider, that will be depend on the diameter of the workpiece, which is called as the pi into d. Whereas the chip length is nothing but after cutting, for one revolution, what will be the length we used to observe for the chip. And finding chip length is very easy task, whereas we are saying width remain constant. This is the width direction. But thickness of the chip will change compared to the uncut chip thickness. With a provided feed motion, we are getting that T1 value. As you said, it is always F cos psi. So someone is asking, sir, question can be asked directly on ASA or ORS system in gate. Whatever system, only orthogonal machining analysis only there is asked. They mentioned even tool geometry in ORS plane. So if they give ORS, then it is better that you are getting the orthogonal rectangle directly. But if they given ASA tool signature and asking a question, then you need to follow the conversion equation between ASA and ORS, right? Where you will not find a orthogonal rectangle. Alpha naught will not be there. So conversion equation between AS and ORS, a very big topic. In a simple nutshell, I can say conversion between AS and ORS will be in the two equations we provide. Together, both two equations we always give in a matrix form. That is, we need to get at the end alpha naught. But ASA system once they given, then we use a back rectangle and then side rectangle. So tan equations we are using to get the conversion. Whereas here in the 2 by 2 matrix, we will be putting a cos psi minus sin psi, then sin psi cos psi. These equations I used to prove in my classes. Whereas if you notice the second equation, tan alpha naught, where orthogonal rectangle we are going to get is nothing but sin psi tan alpha b plus cos psi tan alpha s. So this conversion equation we must use to get the orthogonal rectangle. After that only we should proceed. But most of the time till now history says that in gate examination, orthogonal machining and orthogonal rectangle only they are providing. Like if you notice in these questions, where we will go there for solving. But engineering services, chances are there, they intentionally mention the tool signature in ASA, but you need to calculate the power or total power, minimum power calculations. For that, orthogonal rectangle is required. At that time, conversion equations will be used. In that, it is the second equation, whereas the first equation will provide inclination angle. Whereas inclination angle is cos psi tan alpha b minus sin psi tan alpha s. Whereas alpha b and alpha s are back rec and side rectangle of the ASA, whereas psi is the side cutting edge angle and the inclination angle and orthogonal rectangle. Both we are getting. But the most important is this orthogonal rectangle to perform the analysis. So once we reach to the orthogonal plane and orthogonal rectangle, then analysis will be much easier for us. So after this, in the first analysis, we used to calculate chip thickness ratio where we get the shear angle. The direction of shear we are able to find with a shear angle. So the relation we are always getting as r cos alpha naught by 1 minus r sin alpha naught. These equations we used to prove in our live online classes, even in offline classes, even in recorded version also, you can find all these detailed explanation regarding everything, how the tool look like. Very interesting subject, but initial visualizations for some students find difficult. That's why they feel this content is little difficult. But in reality, once you visualize the things initially, if you reach this particular projection, how the tool and workpiece is reached, how the tool and workpiece appears, then remaining things are very easy and convenient. Whereas with a wedge shape of the tool, as we are considering tip of the tool, that is O, with respect to this point, we do entire analysis. Then first equation where the small r what we are getting is always called as a chip thickness ratio T1 by T2, which is always less than 1 we get. It means because of our assumptions, T1 value, that is uncut chip thickness, is always less than T2 we get. Many reasons, we have big explanation it is, but one common sense is when tool is engaged, width is constant, so the chip which is flowing over the rake face will find difficulty due to frictional force. So that frictional force restrict the length direction, only permission we will be able to get is for the thickness of the chip to get expanded. So thickness of the chip will expand compared to the uncut chip thickness. At the same time, length of the chip will restrict because of the friction force present between chip and rake face of the tool. Now after this equation, we go towards the velocity analysis, where we try to find all the velocities that exist on the orthogonal plane. So velocities we are able to find by considering wedge shape of the tool and the workpiece. Three velocities are existed in the same orthogonal plane. Two-dimensional plane it is. So three-dimensional machining become two-dimensional, where cutting velocity is in this direction, shear velocity in this direction, and chip velocity, which is become now constant. Previously what I said, in the three-dimensional machining, chip velocity is a variable. But because of the two-dimensional machining, it is constant. So at the tip of the tool, if you take all the three velocities, we can frame the velocity triangle where in this direction cutting velocity, and this is the shear velocity, Vs direction. Between these two, the angle whatever we are noticing, we call it as the shear angle, that we are able to find by using this equation. So once you got the shear angle, you know the direction of the shear, whereas this is what a chip velocity direction. Whereas we know the wedge shape of the tool on the orthogonal plane, when we consider, this angle is always a orthogonal rectangle. So here also, when this is orthogonal rectangle alpha, then the remaining will be 90 minus alpha. So when this is a 90 minus alpha, then this will be 90 minus 5 plus alpha. So alpha and 5 get cancelled, 90 plus 90, 180. So that sine rule will provide the relation between all the three velocities. That will be V by sine of 90 minus 5 plus alpha is a cos 5 minus alpha is equal to Vs by sine of 90 minus alpha will be cos alpha equal to Vc by sine 5. So this will be a velocity triangle based, all the three velocities existing on the orthogonal plane. So once we have the velocities, next is a force analysis we perform on the same orthogonal plane. Means by considering same wedge shape of the tool and workpiece, we do the force analysis by considering a chip equilibrium condition which is given by the merchant. So after doing force analysis, we get here at the tip of the tool equilibrium of the chip. Based on that, we draw always a merchant circle diagram where the cutting force Fc is algebraic summation of horizontal component and thrust force Ft is the vertical component of forces. Whereas these two are measurable, but in practically we used to get a shear force in the direction of shearing and normal shear force, which is this direction. This one is Fs and Ns. Both are perpendicular here. And parallel to the rake face of the tool, as the chip is traveling in this direction, so in the opposite direction there will be always a friction force. And then there will be a normal friction force. This is a friction and this is normal friction force. Whereas we can give the relationships between all these dynamic and measurable forces with respect to rake angle alpha, then shear angle phi. Then here we will provide one more extra angle, we call it as a friction angle beta. So for the same resultant, all these forces are making balance. Therefore, we are able to get a all dynamic force calculation based on the merchant analysis. Behind this very big discussion we have, but in a nutshell, I try to tell you that when you try to perform the orthogonal machining, at 100% efficiency calculations are considered by the merchant and provided the relation between dynamic forces and cutting forces. So from here, you can take out many equations in terms of resultant. That is, first of all, cutting force also you can write, that is R cos beta minus alpha, you can write. Right? Cutting force Fc, you will get from the right angle triangle OB and C, you can get this equation. Whereas OAC will provide a shear force and a normal shear force, and ODC will provide a friction and normal friction force. When cutting force Fc is R cos beta minus alpha, thrust force Ft is R sin beta minus alpha. These two equations we get from the right angle triangle OBC. Whereas O is the tip of the tool and OC is the resultant, which is a capital R. This one. So in terms of resultant, we are trying to mention measurable and even dynamic forces. Dynamic forces, shear force also you can write as R cos phi plus beta minus alpha. Whereas normal shear force also you can get, that is R sin phi plus beta minus alpha. And after this, friction and normal friction also we can get, that is R sin beta is a friction force, whereas R cos beta is the normal friction force. So these results we get in terms of the resultant R. Whereas the selected workpiece material always we consider as a rigid isotropic having a shear strength at tau s, not a dynamic shear strength of the workpiece material is also a constant. Practically not possible, but we assume that if the workpiece of having a dynamic shear strength is constant, then we get, because of that assumption, continuous chip formation without any built-up edge whenever tool is engaged. But practically, if you notice, various behaviors of the chip we observe. But to make analysis simpler, we assume workpiece is a rigid ideal plastic material where shear strength of the workpiece is constant. So when shear strength is constant, in this particular plane, which is perpendicular to our screen, there is a shear plane area we get. So shear force in shear force by shear plane area, that's itself mention this shear strength. It means the force required for breaking this unwanted metal, we can calculate that shear force required, we can calculate from this shear strength of the workpiece and shear plane area, that will be in a Newton. Unit will be Newton. So once we have this much idea, then easily 2-mark question we are able to tackle. It's my challenge. You go and check the previous papers. From this much content, what till now we discussed in a fast forward manner in this concept series. Whereas if you notice in a live classes, either it's offline or live online or even in recorded version, we able to go in a elaborative manner, entire discussion in detail, depth of content we try to deliver. And many students who don't even aware about the concept, they try to commit many mistakes. Sometimes formula mugging up may give you answers, but not every time. Especially in a gate examination, whereas it's a aptitude test. Formula mugging will never give a mark. Now, based on this much, if you notice the discussion what we made, the questions, suppose this question observe. Whereas in this question, what they are saying is, under orthogonal cutting condition, the turning operation is carried out on a metallic workpiece at a cutting speed of 4 meters per second. So they provided cutting speed that is 4 meters per second. Right? Cutting speed or cutting velocity they provided. Then the orthogonal rake angle of the cutting tool is provided as 5 degree. So orthogonal rake angle is also provided as 5 degree. Then uncut chip thickness and the width of cut are 0.2 and 3 mm. Uncut chip thickness T1 is, just now we discussed, which is before cutting. Instead of f cos psi or feed value, they provided directly, and even width which is constant, that is also provided, 3 mm respectively. In this turning operation, the resulting friction angle and the shear angle are, just now introduced, those two angles we get, one is first friction angle they given, that is 45 degree, and the shear angle they given, that is 25 degree. On the orthogonal plane, all these things will be on the same plane. If dynamic yield shear strength of the workpiece is 1000, dynamic yield shear strength is also given 1000 megapascal. That is nothing but you can write as directly as Newton per mm square. Then they are asking what is the cutting force, that too in a Newton. To mark this year gate question, where many students used to go only up to the merchant circle diagram and they try to mug up those formulas. Where analysis if you perform, which we used to do in our classes, not only this, we reach in a such a depth that everything we able to provide in detail. Whereas some used to say cutting force they mentioned, right? Cutting force always they mentioned. Yes, most of the time they mentioned, but sometimes if this kind of questions they asked, those who don't have clarity, for them it will be difficult. They feel like the data provided, how we able to calculate. Whereas very simple, cutting force FC is nothing but resultant R into cos beta minus alpha. Whereas resultant R you can replace, if you notice from here, resultant R we can replace in terms of the shear force as R is equal to Fs by cos phi plus beta minus alpha. Whereas shear force also we can replace by using a tau s into As by cos phi plus beta minus alpha. So once we have this much clarity, you replace the resultant directly. That is, instead of R, what we are writing? Tau s into As by cos phi plus beta minus alpha into cos beta minus alpha already there. So if you reach here, then answer is put the data, get the result. Whereas the area of shear plane, which is actually perpendicular, we shown you perpendicular to the reference plane, all the parameters are constant. So once we have this OA value, that is what we call it as the shear plane length in terms of the T1, which is nothing but OA is a shear plane length, which is T1 by sin phi, where angle we able to calculate by using a first equation, then width is constant. Therefore, shear plane area is always a very simple equation, OA into width. Therefore, it's a WT1 by sin phi. So once we have that shear plane area also, then observe here, tau s WT1 by sin phi into cos, already this value is there in the denominator, phi plus beta minus alpha. And along this, cos beta minus alpha. So the people who do analysis, for them, reaching this equation is very simple. So if you try to mug up the first formula, then you will find difficult in solving this question. Now observe, everything is available. Tau is available 1000 into W is available, width of chip and uncut chip thickness T1 is given into cos phi beta minus alpha. Beta is 45, alpha is 5. Both are given by sin phi. Phi is given 25 into cos 25 plus 45 minus 5. 5 plus beta minus alpha. So put the value, get the result. Whereas even if you try to check the units, tau is a shear strength which is in megapascal, nothing but Newton per mm square. Whereas both width and the uncut chip thickness are in mm. So Newton per mm square and these two are mm into mm. So mm square you get cancelled. Remaining everything is angle. Directly you will get these values in a Newton. So tell me in a comment box what is the cutting force value. I hope you understood the type of questions what they ask in a GATE examination. It is not directly formula based every time. Sometime they will be such a logical that without having analysis properly, you are unable to reach to the final answers. But once simple analysis if you make what actually orthogonal machining and what actually the analysis of the orthogonal machining, that clarity you have, then entire this metal cutting subject is very easy. Getting those marks from this subject, %% marks is also very easy. So if you calculate this, so what is the answer, sir? Anurag, I think for your question you got the answer, right? I said they mentioned either ASA or ORS, but most of the time they give orthogonal rectangle itself in the question. So if they provide that, then you know how to proceed with that particular type of question, sir. So answer for this after calculation will be anyone given in chat comment box, try to mention the answer, sir. So if I calculate, I think it's a 2573 Newton. Right? Check it once if I am correct or not. Someone. Okay. So this kind of even few more questions we have, but in the given this time slot, I try to explain what actually the orthogonal machining and recent GATE question. So like this, we have all the content available in our offline and even recorded classes and even in our live online classes. So that's it for today. All the very best for your upcoming examinations. Thank you very much.
My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped me develop a strong temperament required for the exam. My tips for the future aspirants who are preparing for GATE exam will be that you should have a very clear plan and strategy, like how you have to approach the exam, and also believe in yourself and do hard work, because if you have a very good plan and clear strategy, and if you will work hard, you will definitely achieve your goal. Thank you. My name is Gaurav Kumar. I have secured All India Rank 1 in GATE 22 in Electrical Engineering. I was enrolled in ACE Academy offline coaching. The ACE Academy really helped me develop a strong basic required for GATE exam. I was also enrolled in ACE Academy online test series. The questions in ACE Academy online test series were very good and helped